How should we define information? Consider the following observations. You just saw the sun rise in the morning. You would say that you did not get a lot of information from making this observation because it's a very likely event. On the other hand, let's consider this different observation. So you just learned that the winning lottery ticket number is going to be that number. You would say you got a lot of information from making this observation. And the reason you got so much information is that it is extremely unlikely that the winning lottery ticket number will be exactly that. These examples indicate that the definition of information you get from observing an event should be tied to the probability of that event. Specifically, the amount of information obtained should be a decreasing function of the probability. That means the less the probability of an event happening, the more information you get from observing that event. Okay, so what else should we expect from the definition of an information? Let's say you're making two observations, A and B. If there is a strong dependency or correlation between A and B, then the information you get from observing just A alone would be almost the same as that you would obtain when you're observing both A and B. An example of this could be that you're reading two news articles from two different sources which are politically leading in the same direction. So you might as well just read one of them because the other one would be pretty much saying the same thing. On the other hand, if A and B are statistically independent, then the information you obtain from observing A and B should be the sum of the informations you would obtain from observing A and B by themselves. That is why you'll often see like reporters citing, I have confirmed this from multiple independent sources, because the sources have to be independent, otherwise it doesn't count for much. But from the arguments we just made a few minutes ago, we know that the information should be a decreasing function of the probability of the event. That means information from observing an event A should be a function of the probability of A. And if two events are statistically independent, then I of A and B should be equal to I of A plus I of B. This means whatever this function f is, f of probability of A and B should be f of probability of A plus f of probability of B. But we know probability of A and B should be equal to probability of A times probability of B because A and B are statistically independent. This is basically the definition of statistically independent events. Then this equation here turns into this one where f of P of A times C of B should be equal to f of P of A plus f of P of B. What we really have is f of product of two numbers should be equal to f of x plus f of y. Okay. The only function which behaves this way is f of x is a log x, and since we need this to be a decreasing function, we can set a equal to -1. Therefore, the function which most appropriately quantifies information of an event A is information of A should be minus log of probability of A, or equal to log of 1 over probability of A. Note that when a probability of event A is 1, that means you're certain it's going to happen. You won't get any information from observing that event because you already know it's going to happen. And when the probability of event A is 0, that is, it is impossible to happen, then log of 1 over 0 would be infinite. That means you're obtaining infinite information from observing that event, which is sort of absurd because we don't allow P of A to be 0 in this because 1 over 0 is not defined. But what that means is if you think something is impossible and it actually happens, that means your whole worldview was wrong because that is obviously not impossible because it happened. So that means the probability of that event is not 0. So you get into these sort of contradictions. So in this definition, we don't allow P of A to be 0. So we only consider informations about events which are actually possible. When the base of the logarithm is 2, we say that the information is quantified in terms of bits. Now let's look into the idea of how much information do you need to send someone to describe the outcomes of an experiment. So why is this question relevant? Let's say we want to transmit a data file to someone. You actually don't have to transmit the data file as is. You only have to transmit enough information about the data file so that the receiver can put it together exactly. You can view this process as follows. Let's say we are doing an experiment and we are pulling one symbol at a time from the data file, and the symbol you see will be the outcome of the experiment. Then the question is, how much information do you need to transmit to represent the outcomes of this experiment? That is what it means to transmit this data file. In other words, what is the average amount of information in a single outcome or symbol? This will be on average how many bits you have to transmit per symbol. Note that I'm saying on average, that means you don't have to transmit the same amount of bits per every symbol, right? So, but on average, you need to transmit this many amount of bits to transmit one symbol. So what we're really saying here is information content in a data file will be equal to number of symbols in that file times the average amount of information per symbol. It is this average amount of information we call entropy. So now let's formalize this mathematically. Let's say we are doing an experiment, and for each outcome A, we are assigning the amount of information which is a number, which will be equal to negative log probability of A. So the information is acting like a random variable because for each outcome, it's assigning a number. Then the average information would be the expected value of this random variable, or the mean of this random variable, which would be equal to sum of all the values which x is going to take, small x, x times the probability that the random variable will be equal to x, which is px. Right? So this is how we can calculate the expected value of a random variable. So in this case, this sum will be equal to, okay, so we are summing over all outcomes A, so all outcomes in the set omega. And for each outcome, negative log to the base 2 p of A is the information, and we're multiplying by the probability that we'll have that much information, which is p of A. So this will be the average information which we will obtain on average when you're observing this experiment. Let's look at an example. You're doing this experiment where you're rolling a biased 600 dice, which always rolls to 1, right? So now you roll this dice a billion times and you want to transmit what you saw to someone. So you can either transmit a billion once, or you can just say, it's fake, it's always 1. So just write a small message, it's fake, it's always 1. In the first case, you're transmitting a gigabyte of information. In the second case, maybe a few bytes, right? So now, these few bytes will be the same no matter even if this goes to a trillion or 100 trillion or a billion trillion and so on, right? So the amount of information, the average amount of information per roll you're transmitting in this case will be 0. So let's see what is the entropy of this experiment. So I have the rows. So the rows could be 1, 2, 3, 4, 5, 6. And since it always comes up 1, the probability that it will come up 1 is 1, and the probability for all of the rows is 0. So when you're calculating the amount entropy, which is the average information, you use the formula sigma over all values the random variable is taking times the negative log px is the value times the px is the probability. So this is the average information. So basically px values are 1 and 5 zeros. So when the value is 1, you get minus 1 log of 1, and for zeros you have minus 5 times 0 times log 0. So log of 1 is 0, so the first term will be 0, and 0 times log 0. So log of 0 technically is not defined, but when you see x log x, limit x tends to 0 will be 0. So basically we will define 0 times log 0 as 0. So the second term is also 0. So the entropy of this experiment is basically 0 bits. What that means is, in this experiment there is no uncertainty, right? So if the dice is biased in tolerance rolls to 1, so you have no uncertainty in what the outcome is going to be. You're certain it's always going to be 1. That means You don't need any information to convey what's happening. On the other hand, let's say you have a four-sided dice. So when you roll, you can get 1, 2, 3, and 4. And because this is a fair dice, the probabilities for these rolls will be 0.25, 0.25, 0.25, and 0.25. When you calculate the entropy for this experiment, it will be 2 bits in this case. That means on average, you have to transmit 2 bits to represent any single outcome from this experiment. So, and this is, so let's say you have 4 possibilities, and if you want to represent all the 4 possibilities, you need 2 bits, right? So this is the maximum amount of information you will need for this, for an experiment with 4 outcomes, right? So what this tells us, let's say if it's a fair dice and all possible outcomes are equally probable, then this situation represents the maximum uncertainty, right? So anything can happen. And that is when the uncertainty is maximum, and that is when you need the maximum amount of bits to represent the outcomes. So in general, the bounds for entropy are entropy will always be greater than or equal to 0, and it will be less than or equal to log of n to the base 2, where n is the number of outcomes. So first of all, note that in this summation, you have p of x times log of p of x, right? So p of x is positive, and since probability is always less than or equal to 1, log of px will always be it will either be 0 when px is 1, or it will be negative when px is less than 1. So this summation will always be negative or 0. So let's say if it's not 0, it's negative. And then because there's a minus, that means the whole thing will be positive, right? So it can either be 0 or positive, therefore the lower bound is 0. And you will get the lower bound when one of the probabilities is 1 and all others are 0. So when uncertainty is 0, that means the experiment is deterministic. When the entropy is 0, the experiment is deterministic. And that means only one of the outcomes is possible, and you know for certain that's the outcome which you're going to get all the time. On the other extreme, you have the upper bound of the entropy is log of n to the base 2, where n is the number of outcomes. Base 2 means you're measuring entropy in bits. And when the entropy is equal to log of n to the base 2, or its maximum value, that means the experiment is as random as it can be, right? So it's like a uniform over all outcomes. So this is the most random the experiment can be. That means in this case, you have the most uncertainty about what's going to happen. So how does the concept of entropy apply to compression algorithms? So let's say we have a file, and we're doing this experiment where we're pulling one symbol at a time from the file, from the top of the file, and without replacement. And whatever comes out, that's the outcome of the experiment, and we will denote that as omega. So it could be like a sequence of letters, spaces, special characters, and so on. So these are all the possible outcomes, and the set of outcomes is we are denoting as omega. And we can define a probability distribution on all these outcomes. If this file is actually a meaningful data file, let's say text file, then this probability distribution will not be uniform because some letters are more likely to occur than others. For example, E is the most likely letter to occur in English language. So and then different letters will have different probabilities. So we can have a probability distribution on all these outcomes. Then the entropy of this probability distribution will give us the minimum number of bits per symbol. So if the file has a total of capital N characters, then n times h of p is the number of bits you will need to represent that file. So that means any compression algorithm, when it compresses this file, the minimum size of that file will be n times h of p in bits. So let's see if this actually works. So what we're going to do now is generate a random file ourselves with a certain number of symbols and a given probability distribution. We'll calculate the entropy and save those numbers into a file and then compress that file. and see if any compression algorithm can do better than this. So I have my Matlab open here, and in the workspace, there is a variable called R, and you see, if you see that R is of type double, and it has 1 million symbols in it. The minimum value in R is 1, and the max of R value any values in R is 256. And let's say if I find all the unique values in R, like how many different unique symbols there are, and see, so T is of size 256, that means there are 256 unique symbols in there. So if you think of R as the data file, then the big omega has 256 different values, 256 different values starting from 1 ending at 256. The next is, let's look at what is the probability distribution on these different values. I will begin by computing the histogram of R. Let's see, run. H dot values contains the values in the histogram. So I'm normalizing by the sum. So P is basically representing the probability obtained by the empirical histogram. Next, I can calculate the entropy of this probability distribution using this. I want you to pause the video here and make sure that this is the exact formula we have been discussing in our theory. Now, the compressed file size limit will be entropy times the number of symbols divided by 8. So entropy times the number of symbols is the total bits you will need. Divide by 8 will give you the bytes. And let's see. So this tells me that the file size limit is 0.96 times 10 power 5. That means about 0.96 megabytes. If you look at the information about R within the workspace, you will see it has 1 million symbols, but it has, let's see, 8 megabytes. So Matlab is using 8 megabytes of or 8 megabytes to store R, but our compression limit is telling us we only need about 0.96 megabytes. So, and thing is, when we try to save R as a mat file, MATLAB actually compresses the variables and saves it. So what we're going to do is now like try to save R as a mat file and look at the size of the mat file. Before we do that, I also wanted to show you the current entropy of R is actually 7.72 bits. So if you think about, if there are 256 values, then if they're completely uniformly distributed, then because 2 power 8 is 256, you will need 8 bits of information if the distribution is uniform. But because the entropy is only 7.72, it's still pretty uniform, but some variables or some values are more likely than others, so it's less than 8 bits. So I'm going to now save the variable R in a file called random samples. And MATLAB just did its business. So this is the file which MATLAB just created. As I said, it actually compresses before stores. And the file size here is 1.27 megabytes. And we said the compression limit should be 0.96 megabytes. So it came close to the limit, but not very close, because that's a theoretical limit. So, but what we can see is the compressed file size has to be greater than that theoretical limit. Let's say we don't trust MATLAB's compression very much. So let's try to use some other compression file. So or other compression algorithm, I'm gonna make a zip file out of this. And then the zip file is actually slightly bigger than the compressed file. So what that means is you cannot compress it any further. Maybe some other compressed files can do better, but it will always be greater than 0.96 megabytes. So just for demonstrating the theorem, I created another different random R. This time the entropy is much smaller. It is only 2.8. That means it's much less random. And this time, if I calculate the theoretical limit for the compressed file, it comes out to about 0.35 megabytes. Note that the size of R is still same. We still have 1 million different values, But because they're not all as very uniformly distributed, so the entropy is very low. That means this time we will need much less memory to store it. At least that's what the theorem is telling us. So I'm going to save this new R again in the same file called random samples. Let's hit enter. So this time the compressed file size is 529 kilobytes. And note that this is smaller than the previous compressed file size, which was 1.25 megabytes. This is smaller, but it's still greater than the theoretical limit, which is 357 kilobytes, right? So no matter how good the compression algorithm is, it cannot beat that minimum size of 357 kilobytes in this case. Now, if you can come up with your own compression algorithm, which can actually get closer to 357 than 529, maybe your compression algorithm will become very popular.